Hello all, welcome to Tungal online classes. So in the previous class we were discussing magnetism and matter. There we have learned the concept of bar magnet, property of bar magnet, magnetic field lines and property of magnetic field lines. There we have seen that magnetic field lines are nothing but imaginary curved lines which represent the magnetic field of a magnet. The pictorial representation of magnetic field is nothing but magnetic field lines. There we have seen the lot of property of the magnetic field lines. Now today we will see what are the types of magnetic field lines, what is magnetic moment, what is magnetic dipole moment, and how the bar magnet is equivalent to current carrying solenoid. This concept we will see in this class. Now let us take, already we know that magnetic field lines are nothing but imaginary lines, so those represent the magnetic field of a bar magnet or magnetic field of a simple magnet, right? Actually, the magnetic field that can be classified into two categories. One is uniform magnetic field lines and second one is non-uniform magnetic field lines. See here, magnetic field lines can classified into two categories. One is uniform magnetic field lines. Uniform magnetic field lines and second one is non-uniform magnetic field lines. Non-uniform magnetic field lines. Magnetic field lines, right? Now question is how uniform magnetic field we can represent and how the definition we can see. Uniform magnetic field lines mean the magnetic field whose magnitude and direction must be same at every point. Such magnetic field lines we are calling uniform magnetic field lines. See here, uniform magnetic field mean at every point it should be have the same value and same direction. This uniform magnetic field we can represent in three ways. Uniform magnetic field, either it can represent by set of parallel lines. Set of parallel lines mean equidistant parallel lines. See here how uniform magnetic field lines can represent. See here, uniform magnetic field lines can represent by set of equidistant parallel lines. This I can call uniform magnetic field lines. So this indicates at every point the magnitude and direction of magnetic field must be same. This is one way we can represent uniform magnetic field lines. But if the magnetic field is uniform and that magnetic field is directed into the plane, then how to represent? See here, for example, the magnetic field is uniform and that magnetic field is directed into the plane. This board is a plane. If the magnetic field is uniform and those magnetic field, how they go? They go into the plane. How to represent that magnetic field? See here, uniform magnetic field we can represent like this also. This indicates that this magnetic field is uniform and this magnetic field is directed into the plane. This is the one way we can represent uniform magnetic field. These magnetic field lines are going like this. But we can represent in alternating way also. If the magnetic field is uniform and directed out of the plane. Out of the plane mean like this. See here, the magnetic field is uniform and it can going away from the plane. How to represent that? See here, if the magnetic field is uniform and that magnetic field is going out of the plane, like this you can represent. See here, like this. This represent magnetic field is uniform and this magnetic field is directed away from the plane. Simply I will show how the magnetic field can represent uniformly. This indicates, above figure indicates magnetic field is uniform directed into the plane, and this indicates magnetic field is uniform and directed out of the plane. So these are the three ways in which uniform magnetic field we can represent. Then come to the point non-uniform magnetic field lines. Non-uniform mean the magnetic field whose magnitude must be same but have different direction, or else the magnetic field whose magnitude and direction must be at different point. Those we are calling non-uniform magnetic field. See here, generally how to see non-uniform magnetic field? Simply I can show. Non-uniform magnetic field can be represented like this. Either they can represent like this. Look at me. This represent non-uniform magnetic field lines. So what about the direction? Direction must be represented like this. Are you following this? This is non-uniform magnetic field. Or the non-uniform magnetic field can represent like this also. This can represent. This indicates non-uniform magnetic field lines. I mean, the magnetic field whose magnitude and direction must be at different point. So that we are calling non-uniform magnetic field. Students, in the previous class, already we defined pole strength. Pole strength means the ability of the magnetic pole to attract the magnetic materials like iron, nickel, cobalt, zinc, etc. That ability we are calling pole strength. Already we know that. The pole strength can be represented in terms of end of the magnet. I mean, pole strength situated near the end of the magnet, but not exactly at the end of the magnet. Already we know that. Our point is, we should know magnetic dipole and magnetic dipole moment. This concept we will see. So here, concept is magnetic dipole, dipole and magnetic dipole moment. Magnetic dipole moment. See here, this concept we will see in detail now. What is magnetic dipole, how magnetic dipole moment is there, and how to represent this physical quantity. See here, already we know that a bar magnet, already is here, the bar magnet, it is a rectangular cross section object having north pole and south pole. This is the bar magnet. What I can call? This I can call north pole, right? This you can south pole. The imaginary line joining from north pole to south pole, this we are calling magnetic length, right? Here, how to define pole strength? The ability of the magnetic poles to attract magnetic materials like iron, nickel, cobalt, that we are calling pole strength, right? Every magnet has equal pole strength but opposite in direction. Already we know. See here. Point is, what is magnetic dipole? Magnetic dipole means the pair of equal and opposite pole strength. Pair of equal and opposite pole strength separated by small distance. Already we know in electrostatics. In electrostatics we define electric dipole. Then how to define that? The pair of equal and opposite charges separated by small distance. Similarly, you can define your magnetic dipole. Magnetic dipole means the pair of equal and opposite pole strength. Pair of equal and opposite pole strength separated by small distance is called as magnetic dipole. I mean, every magnet, either bar magnet, either U-shaped magnet, either magnetic needle, or the magnet cut into so many pieces, each magnet is act as a magnetic dipole. Are you following me? Each magnet is act as a magnetic dipole. So that magnetic dipole means pair of equal and opposite pole strength separated by small distance. Then point is, what is magnetic dipole moment? Magnetic dipole moment. Magnetic dipole moment means, see here, the product of either pole strength and the distance between two pulses. That we are calling magnetic dipole moment. Look at me. Magnetic dipole moment can be represented by quantity capital M. How it is? Magnetic dipole moment is product of either pole strength and distance between two poles. Product of either pole strength and distance between two poles. Product of either mean either you can take a north pole strength or you can take a south pole strength. Product of either and distance between two poles. This we are calling magnetic dipole moment. This magnetic dipole moment is similar to electric dipole moment. There in electrostatics, how to define electric dipole moment? The product of either charges and distance between two charges. Similarly here, the product of either pole strength and distance between two poles. This we are calling magnetic dipole moment. In electrostatics, what we have learned, electric dipole moment is a vector quantity. How to take the direction? Direction must be taken from negative charge to positive charge there. Similarly, magnetic dipole moment, it is a vector quantity and direction must be taken from south pole to north pole by convention. How to take here? Magnetic dipole moment, it is a vector quantity. It is a vector quantity and the direction must be from where to where? Direction must be from south pole to north pole. How it is? See here. So it is a magnetic dipole. Here equal and opposite pole strength are there. How to take the direction of magnetic dipole moment? So from south pole to north pole. This is nothing but vector quantity. I mean direction must be from south pole to north pole. This is in case of magnet. But magnetic moment we can define in case of current carrying coil also. In case of current carrying coil, how to define magnetic dipole moment, that is important here. See here. Now shall I take a coil? The coil carrying current. Look at my students. Now can take, see here, this is nothing but coil. This is the coil. So in this coil this much current is carrying. Are you following me? And this coil has how much radius? So it has this much radius, capital R. Right or wrong? In moving charges and magnetism previous chapter, we have learned that how to define magnetic dipole moment. We have learned the concept atom as a magnetic dipole moment. In this case, how to define magnetic dipole moment? Students, in case of current carrying coil, magnetic dipole moment can be defined as the product of current and surface area of the coil. Product of the current and surface area of the coil. See here surface area of the coil, how to define? Surface area of the coil is nothing but circle and that can be represented by area cross section phi r square. Are you following this? Then if this coil contain how many turns? If this coil contain many turns, say it contain n number of turns. For n number of turns, how to represent? Represent by small n. Or it can total number of turns can be represented by what value? Capital N. In case of magnetic moment, magnetic dipole moment can be represented by product of either pole strength and distance between two poles. On other hand, in case of current carrying coil, magnetic dipole moment is product of current and surface area. When current is carrying in the coil, one end acts as south pole, another end acts as north pole. Already we have learned in the previous chapter, moving charges and magnetism. But see here, by taking the concept of magnetic dipole moment, we can see one more important concept, the bar magnet and current carrying solenoid. Already we know that in the last chapter we have learned a solenoid, the coil with many number of turns wounded on insulating wire, that we are calling solenoid. And in the previous video what we have learned, that magnetic field of the bar magnet. So if a small iron piece are spreading around a bar magnet, they will arrange around a bar magnet in a different pattern. Those pattern indicates the magnetic field of the bar magnet. Similarly, if we plot the magnetic field of the current carrying solenoid and magnetic field of the bar magnet, how they looks like, that will see students in detail. Our concept is now bar magnet is equivalent to current carrying solenoid. That concept we will see. See here. Concept is look at it. Our concept is now bar magnet is equivalent to current carrying solenoid. Bar magnet is equivalent to current carrying solenoid. See here. Look at me. How both are equivalent? Students, separately I will draw the diagram for both bar magnet and current carrying solenoid. Shall we see here? So we can call this is a magnet. This is bar magnet. So this bar magnet consists of north pole and south pole. Right or wrong? How the magnetic field lines are there? Outside from north pole to south pole, inside from south pole to north pole, like this. Like this, it exists. Are you following? How they will go? So they must be go like this. Magnetic field lines of the bar magnet already you have seen the last class. How the direction must be? Outside from north pole to south pole, inside from south pole to north pole, like this. Like this cases. Like this can see. This is the bar magnet, magnetic field of the bar magnet. And we know solenoid. What is the solenoid? The coil with many number of turns wounded on an insulating wire, that we are calling solenoid. How it is looks like solenoid. Look at me here. The coil with many number of turns. The coil circular coil with many number of turns. Like this. So at one side current is carrying, on another side current is leaving. Are you following me? Right or wrong? If you spread iron pieces around this current carrying solenoid, they will arrange in a definite way. How they will arrange? In what pattern magnetic field has exist around given bar magnet, the same way that iron filings are arranged around current carrying solenoid. How they will arrange? If I take very small pieces of the iron and I will spread it around given current carrying solenoid, how they will arrange? They will arrange in a definite way. How they will arrange? Like this they will arrange. Like this they will arrange. In this way they will arrange. Like this pattern. Like this pattern they will arrange. So if we join all the imaginary lines of the iron filings around given current carrying solenoid, that is equal to the magnetic field of the bar magnet. Like this. Like this I can arrange. So how the direction must be? So then it is act as north pole, this is act as south pole. Magnetic field lines can be must be like this. Inside, this is the outside. So inside must be like this. If you observe both pattern, the pattern of magnetic field of the bar magnet and magnetic field of the current carrying solenoid, the both pattern looks like the similar. From this you can confirm the bar magnet is equivalent to current carrying solenoid. Even though in practice we need the mathematical treatment. How mathematically we can see bar magnet is equivalent to current carrying solenoid. That concept we will see. Before that I can take a magnet, bar magnet I will take. This is the bar magnet. So this is north pole and this is the south pole. This is the imaginary line from north pole to south pole. Right. And this is axis of the bar magnet. On the axis of the bar magnet, at any point if we calculate magnetic field, at any point if we calculate the magnetic field, that magnetic field value must be equal to 2m divided by 4 phi into how much? R cube. This is what? Magnetic field of the bar magnet along its axis. Right or wrong? Similarly, if you found magnetic field along the axis of the current carrying solenoid and that value must be equal to this value, then you can treat that the bar magnet is equivalent to current carrying solenoid. Right? So on the axis of the bar magnet, how much magnetic field we are getting? B is equal to 2m divided by 4 phi. 4 phi into R cube, where m represents magnetic dipole moment, R represents distance at which we are calculating magnetic field lines, value of the magnetic field. Let us prove along the axis of the bar magnet we found this much value of magnetic field. Then along the axis of the current carrying solenoid we must be found the same value. Then you can treat that the bar magnet is equivalent to current carrying solenoid. Right? That we are going to prove. Let us prove along the axis of the current carrying solenoid we found the value that must be equal to this one. That B is equal to 2m divided by 4 phi into R cube. Right or wrong? See here, let us see that. This is mu naught value actually. Mu naught by 4 phi, 2m divided by R cube. Right? So let us see that. Let us see along the axis of the current carrying solenoid, how we found the value of B is equal to mu naught by 4 pi 2m divided by r cube. That we'll see now. Look at me. See here. Right? Let us go how to prove. Before that, shall I take a current carrying solenoid? I can take this nothing but current carrying solenoid. Right? So in this current carrying solenoid, this much current is carrying, this much current is carrying, like this way current can carry, right? This much current can leave. Are you following me? Right? The current carrying solenoid is made up of many number of circular turns. It contains many number of circular turns. Are you following me? According to Biot-Savart law, application of Biot-Savart law, on the axis of the current carrying solenoid, on the axis of a current circular loop, we found magnetic field. Actually, see here, this is one circular loop. So this circular loop contains how much radius? It contains this much radius. We found along the axis of the current loop, current carrying loop, we found magnetic field. How much magnetic field we found? B is equal to what value? B is equal to mu naught phi r square n into 2 divided by how much? 4 phi. Then r square plus x square raised to how much? 3 by 2. Where it is? Along the axis of the current carrying loop. According to Biot-Savart law, what value we found? B is equal to 2 mu naught phi r square n divided by 4 phi r square plus x square raised to 3 by 2. Correct or wrong? See here, I can take any cross section of the solenoid. How to take the cross section of the solenoid? I need cross section of the solenoid must be like this. Shall I take this cross section of the solenoid in this way? Right? Separately shall I draw? I need along the axis of the current carrying solenoid, I need magnetic field. That value I need. See here. Shall I take here? Separately I will take. How it looks like? It looks like cylindrical shape. Shall I draw it separately? So I can take nothing. This is nothing but a cross section of a current carrying solenoid. Cross section of the current carrying solenoid. Are you following me this? This one I can need. Right? So how this shape looks like? This shape must be looks like this. Look at me. This is nothing but the solenoid. Need on this solenoid. Look at me. On this solenoid, how to take? This is nothing but a cross section of the solenoid. Are you following me? Cross section of the solenoid. Right? And this is nothing but axis of the current carrying solenoid. Are you following me? And this is nothing but a vertical axis I can take. Right? Are you following me, students? I can take this nothing but center of the solenoid. I can take this point is nothing but O point. And from center to this point, I am taking the length is L. Length is L. Again from center to this point, again I am taking the length is L. Total length is 2L. Total length is 2L. So on this current carrying solenoid, I take any point along its axis where we need to calculate magnetic field. See here, which is the axis? I can take this nothing but axis of the current carrying solenoid at this point P. At this point P. From center of the current carrying solenoid, I need magnetic field. At what distance? Smaller distance. Are you following me? Right. Then I need any circular element on current carrying solenoid. How to take the circular element? I can take circular element must be like this. See here, this is nothing but circular element on a current carrying solenoid. This circular element has how much thickness? Let us take the circular element has the thickness how much? I can take this is equal to dx value. So thickness is equal to how much? That equal to dx value. And the circular element from this center, how much distance available? X distance available. Right. Then this is R. from center of the current carrying solenoid to point where we need magnetic field is nothing but r, and this is x. What is remaining? This remaining is equal to how much? It is r minus x. Are you following me? Right or wrong? Already we know that the current carrying solenoid is made up of many number of circular turns. For one circular turn, how much magnetic field is there? This much magnetic field. What is the value of the magnetic field? I found that value of the magnetic field B is equal to what value, or dB is equal to what value? dB is equal to 2 into mu naught phi r square whole divided by how much? 4 phi into how much? R square plus x square raised to how much? 3 by 2, right? Where r represent the radius of the circular coil. I can take here, or you can take here, or here, no matter, right? How much current is carrying here? Let us take this much current is carrying. This much current is carrying here. Are you following me? Then for one circular turn we need this much magnetic field. But here I need the distance. Due to what distance? I need the distance from circular element to the observation point. From circular element to observation point distance is what? R minus x. So that simply I will represent this x value. X value by what value? Shall I take? Magnetic field can be represented by what value? R minus x whole square of how much? Raised to 3 by 2. Right? Because of I need only this distance, r minus x. But look at me, students, the observation point small r is very greater than the distance x and the radius r. Are you following me? What I am saying? The distance small r must very greater than the distance x and the radius r. So that whatever the denominator is there, in the denominator small I and x is very smaller, very smaller, so that the small r is considered and capital R and small x can be neglected, because this value small r is very greater than x and very greater than capital R. Simply in the denominator whatever capital R and x must be neglected. Then what we found? We found that so dB is equal to what value? dB is equal to, and due to this circular element, how to multiply? Due to this circular element I can multiply by what value? Dx. And it contain how many number of turns? It contain n number of turns, because it made up of many number of turns. Right or wrong? Then if small r is very greater, capital R is very small, small x is very small, then small capital R x is neglected. What is remaining then? 2 into mu naught into phi r square into into n into dx whole divided by how much? 4 phi into what value? R cube. Because x neglected, r neglected, r square goes, and r raised to square raised to 3 by 2, that becomes r cube only, right? But the circular element you can take at this point, you can take at this point, you can take at this point or this point. How to take the line? Along positive x I can take the capital L, small l, and along the negative x I can again the minus small l. So that circular element can be added for overall circular element and overall current carrying solenoid. To add all circular element, just I want to make it integration. I mean total magnetic field, how to form? Total magnetic field simply I can represent B is equal to integral of dB from where to where? From minus L to plus L. Because along positive x-axis I can take small l, along negative x-axis I can take minus L. Length can be added from minus L to plus L. Then what this equation becomes? Total magnetic field. What is dB? This value. Then what we found? B is equal to what value? Integral of from where to where? From minus L to plus L. What about this value? 2 into mu naught into how much? 5 into r square into n into dx whole divided by how much? 4 5 into how much? That becomes r cube. Right or wrong? So all are constant. 2 is constant, mu naught constant, phi constant, r constant, n constant, 4 phi also constant, r cube also constant, variable only dx. So shall I cut only one step here? Look at me, how to find this value? This value B is equal to what value? B is equal to, what are constant values here? Constant value 2 mu naught constant, phi constant, r square also constant, n also constant, divided by 4 phi, r cube also constant. What is variable? Minus L2 plus L, which is variable only, dx is variable, right? Then make it integration. B is equal to what value? B is equal to 2 into mu naught into phi into what value? R square into n whole divided by 4 phi into r cube. Integral of dx is equal to x from where to where? From minus L to plus L. Upper limit L of L minus of minus L. How this value becomes B then? Look at me. How to find? B is equal to what value then? 2 into mu naught phi into how much? R square into n whole divided by 4 phi into r cube. This one becomes what value? 2L, right? Already we found that how to define magnetic dipole moment in case of current carrying coil. In case of current carrying coil, how to define? Look at here. In case of current carrying coil, magnetic moment is equal to product of current into area. Are you following? But area looks like a circle. Area of cross section how much? Area of cross section is equal to what value? Pi r square, right? It contains how many number of turns? It contains n number of turns, right? It contains how much length? L and L. What is total length? That is total length is equal to what value? 2L. Then what is capital M? I phi r square n into 2L. I phi r square n into 2L. That is nothing but capital M. Then how to find? B is equal to 2 into mu naught into what value? Capital M whole divided by 4 phi into r cube. Along the axis of the current carrying solenoid, we found this much value, and this value is equal to current carrying. This value is equal to magnetic field of the bar magnet along the axis of the bar magnet. Along the axis of the bar magnet, we found the same value, and along the axis of the current carrying solenoid, we found this the same value. Then from this what you can confer? Bar magnet is equal to current carrying solenoid. But 2 points you can confer. By taking the pictorial representation of the magnetic field of the bar magnet and magnetic field of the current carrying solenoid, from this you can confer, or mathematically along the axis of the current carrying solenoid we found the magnetic field this much value. The same value can found along the axis of the bar magnet also. Then from this you can confer bar magnet is equivalent to current carrying solenoid. So up to here today's class has over. Remaining concept we will see in the next class. Thank you guys.